The question we are solving now belongs to test series 6. It is of control system subject. In specific, it belongs to liquid analysis. The question is a linked answer question. As per the question, there is a unity negative feedback control system. This system gives an output of y of t is equal to 2 times e power minus t sin t for an impulse input. As per the question, we need to find the gain margin in dB and phase margin of this control system. From the linked answer question part 1, we already got that the forward path transfer function of the control system can be written as 2 divided by s into s plus 2, which is equal to the open loop transfer function due to the reason that the system has unity negative feedback. Now, upon substituting s is equal to j omega, we see that g of j omega multiplied by h of j omega can be written as minus 2 omega minus 4j divided by omega multiplied by 4 plus omega square. So, for finding the gain margin, we need to find the phase crossover frequency, which can be obtained by equating the imaginary part of g of j omega multiplied by h of j omega to 0. Upon doing this, we see that the phase crossover frequency of the system tends to infinity. So that is, the phase crossover frequency is located at s is equal to j infinity. From this we can see that g of j omega multiplied by h of j omega is equal to h of j omega tends to 0 as at s is equal to j infinity. So the gain margin can be written as 20 log 10 maps of 1 by g of j omega p multiplied by h of j omega p. This is equal to or tends to infinity at the phase crossover frequency of infinity radians per second. From this we can see that the gain margin of the control system is infinite dB. Now we need to find out the phase margin of the given control system. For finding the phase margin, we need to find the gain crossover frequency, and we know that at gain crossover frequency, abs of g of j omega multiplied by h of j omega is equal to 1. So it implies 2 divided by omega g multiplied by square root of 4 plus omega g square is equal to 1. So upon simplifying this, we see that the gain crossover frequency of the system can be written as omega g is equal to square root of 2 multiplied by root 2 minus 1 radians per second. So we know that the gain crossover phase margin is equal to 5 plus phase of g of j omega g multiplied by h of j omega g. That is, the phase evaluated at gain crossover frequency needs to be added with phi to get phase margin. So which upon simplification we see that can be obtained as pi minus tan inverse of square root of 1 by root 2 minus half. So this is the phase margin of the control system. From this we see that the obtained gain margin and phase margin correspond to the options D.